Okay, today we're going to talk about nuclear half-lives and carbon dating, and most of this should be pretty accessible, pretty easy to follow. If you're unsure about any of the parts of it that we kind of build up to, you may want to take a look at the prior video. This is a screenshot from the YouTube. If you're looking at this on Google Classroom, it's going to have a slightly different title, but be very easy to find. So we want to start out by asking, how long do radioactive isotopes, that is radioisotopes, stay radioactive? And how can you tell? Well, it depends on the radioisotope. Some of them hang around for a pretty long time, as you can tell by these storage barrels, and some hang around for a really, really long time, as you can see if you've read anything at all about the Chernobyl disaster. Now, this isn't an anti-nuclear power diatribe, but it'd be kind of silly not to mention that in that context. There's other ones that don't hang around very long at all that can actually be used in medicine. And that's what this next part is about. Here's a kind of a diagram of a scan that is done in hospitals sometimes. Probably the best known use of isotopes radioisotopes in medicine is when a doctor will inject radioactive iodine into a patient to tell whether or not the thyroid gland is working properly. And if it is, they'll be able to see an image that lights up in the middle of the throat where the radioactive iodine is being accumulated by the thyroid gland, and they'll get an image like this, which is much less dramatic than the image on the left-hand side. Anyway, another thing that usually people will talk about sometimes if they're talking about the length of how long radioisotopes will hang around is talking about Marie Curie's notebooks. Marie Curie's lab books, they're still radioactive, and that's from the late 1800s, early 1900s. She passed away in, I think, 1930-something. But anyway, the work that she did with those was more than a century ago, and they're still radioactive, and the most optimistic estimate of how long they'll stay radioactive is about 1,600 years. Talking about even longer, the Chernobyl disaster that I mentioned a little while ago, some of the isotopes that were thrown out into the environment are not going to decay for another 20,000 years or so, down to background levels. Now, just real briefly, that was not a nuclear explosion. It was actually a conventional explosion with radioactive material, thrown out. So it's a kind of common misconception that nuclear power plants can undergo a nuclear explosion. They can't, but they can spray some pretty nasty crap out if something like that does happen. There's also even longer lasting isotopes for even millions or even billions of years, but that's a little probably outside the scope of some of the things we're going to be talking about here. So all these things do have one thing in common. They all decay with predictable patterns, so the same sort of patterns, which lets us make all sorts of useful predictions about their behavior. Just about any radioactive isotope will decay with the pattern that's shown here. It's referred to as exponential decay, where you have a loss rate that's proportional to whatever the current value is. That means, as it says in the text up here, the more you have, the faster the loss rate, and as the amount decreases, the rate of loss decreases. So you have basically what amounts to time, what is time, on the x-axis, and then you have the percent remaining on the y. We're going to talk about what a half-life is in a minute. And you see how the curve drops off really sharply at the very beginning. You lose most of it at the very, very early parts, and then it flattens out to a lot shallower curve toward the end. And this pattern can be best described, or most frequently described, by the concept of a half-life, which is the time it takes for half the radioisotope to decay and become another isotope. So if you'll see here where this 100% mark is, in the first half-life, it'll go down by 50%. Now the next part, people should probably pay really close attention to if they've not seen this before. The most common mistake in comprehending this stuff that me and pretty much anybody who's ever taught this stuff sees in beginning students, the most common mistake in the understanding is this. Okay, it goes down by 50% in the first half-life, and then the second half-life, of course, it loses another 50% and then goes down to 0, which, of course, is completely untrue. That doesn't happen. It doesn't go from 100% to 50 and then 50 to 0. Half is lost in the first half-life, and then another half is lost in the second. And then, so it goes from 50 down to 25%. And then, of course, it goes from 25% down to 12.5, which is another half. And then from 12.5 down to 6.25. So it gets less and less every time. Down, we'll stop at 5 half-lives, down to 3% and something. So anyway, so it shows this pattern, in regardless of any isotope, any radioisotope that you deal with. They all show the same sort of decay. And the question is, why does this happen? What determines this? And it's because each isotope has this unique ratio of neutrons to protons. Remember, if you saw the last video, you remember that we talked about how the neutron to proton ratio determines the stability, or that is the activity, of an isotope. And since each isotope has a unique ratio of neutrons to protons, then the isotopes are going to have different levels of stability, and that means they're going to decay at different rates, and they're going to have different half-lives. Now, just as an aside here, a fairly important aside in other areas of science, there's other things like drugs, toxins, anything basically that has any type of biochemical laws, and there's other types of laws too, but they're all measured in half-lives. So you can see this table here that I've made with, or that I copied from benzodiazepines, things like Xanax and Valium and things like that, and those aren't the only drugs. Practically all drugs are measured with half-lives. They show the same sort of laws. The main difference, though, is in real life, the patterns are going to be a lot more complicated, and there's going to be a lot more variability in it compared to the very predictable patterns of the isotopes. You can see some of these drugs have a half-life that really, really varies, so that's a good bit less predictable than it is with isotopes. It says here about how there's not a way to calculate radioisotopes half-life from other factors. In other words, in most cases, the isotope's half-life is going to have to be given to you. So, and from stuff that's already well known. Here's one of sulfur-35, which I used to work with quite a lot. It breaks down into chlorine plus a beta particle. And the half-life for sulfur-35, which you would not be able to calculate on your own, using any of this, is 86 days. That's going to have to be given to you. It's 86 point something, but 86 days is going to be good enough for what we need. So by the first half-life, when 50% of the S35 is going to be decayed, it's going to be at 86 days. The second half-life, when it's down to 25%, is going to be 172. Third half-life, 258, and on and on. I'm not going to go out past 5 half-lives again. So, and of course, that would vary depending on whether or not you're talking about sulfur-35 or not. One other brief thing I want to show, just with regard to how we use some of the symbols. Most of the time, when you're not dealing with an equation like this, or you're actually doing a little bit of simple math, most of the time you'll see the symbol written that way, and that way with all the other isotopes too. It's just easier to do. It's easier to deal with the Microsoft Word, and also just in a regular old lab notebook, because, I mean, if you think about it, putting a 16 there and putting an S there is a little bit redundant. There's only one element in the entire universe with 16 protons, and that's sulfur. And then, of course, we're using the symbol for sulfur anyway, so that's, if you're not doing the math, that's a little bit redundant. It's usually just done just like this. Okay, so if you want to calculate the actual values of the radioactivity, instead of just reading it off the chart, you can use this equation, which is actually more scary looking than it actually is. The A here is basically the amount at whatever time that you want to calculate it. The A sub 0 is the initial amount. You just basically take that and multiply it by 1/2 to the n power, the n being the number of half-lives. And again, it looks kind of scary, but I usually try to break it down and show a more simplified version. The example that I'm going to use for this one is with tritium, which is a radioactive form of hydrogen with a half-life of 12.3 years. And anyway, as an example problem, which you, again, is oversimplified probably, say you want to do a problem, how much of 1,000 dpms, which is disintegrations per minute, would be left after 3 half-lives. So this is just a way of examining how the equation works more than really about solving a problem. You have the equation A sub 0 times 1/2 to the n. So you plug in the numbers here, and you can solve it this way. You can plug it right in and solve it. But also, please notice the reason I'm doing it this way is because it's exactly the same as doing it like this. 1,000 DPMs times 1/2 times 1/2 times 1/2, which is equal to 125 DPM. So 1,000 DPMs divided by 2, which is 500, divided by 2, which is 250, divided by 2, which is 125. That's mathematically exactly the same thing. It's kind of drawn out more simplified, but it's really just more to make a point. Another example of what you might want to kind of walk through here: how many half-lives would it take to get below background? Background being spelled out up here, 25 DPM. All right, so that's just the natural background radiation you would run across every day. So how many half-lives would it take, and how many years is that? Well, you can follow it out the same way with one little wrinkle: 1,000 DPMs times 1/2. So all you have to do is keep up with the number of times you're dividing it. Times 1/2, times 1/2, times 1/2, times 1/2, and then one more times 1/2. So we have to do that 6 times to get down below background, which is 16 DPMs. All right, so how many half-lives would that be? 6. How many years is that? Well, 6 times the half-life, which is 12.3 years, which is 73.8 years. Now, the problems are not work that way in real life. They're just not. For nothing else, it never comes out to exactly, a specific number of half-lives in whole numbers. It just doesn't. But this is just shown. I just went through this just to show how the equation sort of works. So on that one, don't tell anybody that I worked it out like that. Not really. I'm putting this on YouTube, but again, it's useful for illustration, not really for working the problems. The way it's done really in real life is more like this. Say if you spill 5,000 DPMs of a tritium-containing sample on a counter without knowing it contained tritium, and that's a real danger sometimes, how many DPMs will still be there if someone tests the counter for radioactivity 30.75 years later, so 30 3/4 years later? And again, just a reminder, the half-life for tritium is 12.3 years. So use exactly the same equation no matter what isotope you're using, no matter what radioisotope, what radioactive compound. And the main problem that people run across when they're working this for the first time, when they're new at this, is making the mistake right there. All right. N is in number of half-lives. Okay, it is not in the number of years. And you could see that be a pretty common mistake. In fact, it's the most common on a problem like this. So you need to convert years into half-lives before solving the equation. All right, so this is 1 half-life. So you just basically make a fraction with that as the denominator to figure out how many half-lives total. So what we have is 30.75 years, and you want to divide that by 12.3 years, and that comes out to 2.5 half-lives. All right, so then we can plug that in to the end. So 5,000 DPMs times 0.5 raised to the 2.5 power comes out to 885 DPMs. And when plugging this to the calculator, I always like to do this part first. Just take 0.5, raise it to 2.5 power, hit equals, and then multiply it by 5,000 DPMs. It lessens the chance of making a calculator error or an order of operations error or something like that. I always do the most complex one first. Okay, we're going to see what this looks like graphically. As I mentioned before, the isotopes, the radioisotopes, all follow the same curve. It's just a matter of how long the half-life is, that all the half-lives are going to be different, but the shape of the curve stays the same. So if we did start out with 5,000 DPMs, it'd be pretty easy to figure out that after 1 half-life, in this case 12.3 years, you'd get down to 2,500 DPMs. After another half-life, you divide that by 2, it'd be 1,250. And then here's the math that we did, 885 DPMs, which if we carry this on further, just dividing by 2, 1,250 divided by 2 is 625. Now, you might at first think that you could just find the midway point between 1,250 and 625 and do it that way. It'd be a lot easier. It turns out that won't work because that curve is not linear. If you did that, it would come up with something. You'd come up with something like 938 DPM or something, which is significantly off. So anyway, that's just to show that the math we came up with, the math that we just got through working, fits the curve. It falls on the curve just perfectly. So we just carry it on out to the last bit just to compare with some of the others. Remember before how the S-35, the fifth half-life on that was something like 14 months. It ended up being about 430 days, I think. And here we're all the way out to 61.5 years.